In this video, I'm going to go through the idea of standard deviation that we're going to see in quantum mechanics. And you might be familiar with standard deviation from different classes, statistics, experimental measurements, and in here we're going to be thinking about RMS, so root mean square. And it's important to note that most of the work we're doing in this class is not experimental, it's theoretical. So when we run our spin simulation, maybe then you could repeat the measurement over and over and over again and actually calculate a standard deviation from a list of numbers. But in general, we're going to be calculating a predicted, a theoretical spread, which again, we'll think about this in terms of RMS, root mean squared, of a theoretical distribution. And so one way to think about this is that there's going to be distributions, and right now we're talking about discrete systems where there's just some specific values the measurement can yield, but eventually we'll move into generalized, so continuous distributions. So imagine a distribution of energy, and this could be like a histogram where there's only specific values, or a continuous distribution as I've drawn. Now these two distributions, to the extent that I can draw them, have the same average value. Remember, that would be expectation value. And then there's a distribution around that. It isn't necessarily the case that every single measurement will yield the same value. And so how kind of narrow versus wide this distribution is, we're going to capture with this thing we can call standard deviation or RMS. And the way we're going to denote it is delta whatever. And in this case, energy is what we're measuring. Energy would be our operator, so we would say delta E. And triangle is capital delta Greek letter, so that's why we say delta E. So in intro physics, delta means change of. That isn't quite the meaning here. Again, now we're meaning standard deviation, and in this case specifically RMS. So one way to calculate standard deviation, and again the definition we're going to use for quantum mechanics is given here. And we have to unpack this a little bit, and it's really important to understand what our notation means, because we've really captured a lot here, and if you're not comfortable with the notation yet, this can look meaningless. So this term here is the expectation value of our operator, and this is going to have to be for some sort of system, right? So this isn't just every measurement of energy we could possibly make. This is for a specific system. So we need to be talking about, when I say a system, a specific state. So when I write this, we remember this is expectation value, which we can calculate for a specific state this way. We're then taking this, which will be some scalar number, and if it's an observable, it will be a real number, and then we square it. Okay, what's this term? Now you might go, oh man, let me just pull the square outside. That is absolutely not how this works. This literally means the operator squared. So you have to calculate that as like this, where you've squared the operator and then you're finding its expectation value. And so if our operator is a matrix, this is squaring the matrix and then doing this work. And there's certain things you can think about in terms of, okay, if it's a Hermitian operator, what is this going to mean? We're not worried about that right now. But it's important to see that this isn't going to always give you 0. There are cases where this can result in 0, but it's not always going to result in 0. So we're calculating this for a specific operator, meaning a specific measurement. A is our general thing, but this could be like spin in X, for instance, and we do have to apply it to a specific state. So I'll go through some examples of this, because where this is going to have some unique meanings in quantum mechanics is thinking about uncertainty, and for instance, the uncertainty principle. So we have to introduce some other ideas first, but this equation is really key, and it's important to understand what this notation means.